So if we have three objects floating in space, three asteroids as this question says, can we determine the net force on each asteroid? So remember, any two objects that have a mass are going to exert a gravitational force on each other. So for example, asteroid A will exert a force on asteroid B, and then asteroid B will exert that same force back on asteroid A, right? So what we could do is we could label that force as this is the force of B on A, and this is the force of A on B, right? So can we find the magnitude of that force? We can, right? Any two objects with known mass and known distance, we can use Newton's law of universal gravitation, right? To find the magnitude of that force between them. So the force of gravity between them is just going to be equal to capital G, m1, m2 over r squared, right? And for the force B on A or A on B, we'll just label this as A and B, the force between A and B here. So it's going to be 6.67 times 10 to the negative 11. M1, so the mass of A is 2 times 10 to the 7. So we'll do 2 times 10 to the 7. And M2 is 1 times 10 to the 7. And the distance between them is 10 meters. So we'll do 10, and don't forget to square it. That's a very common mistake, is you forget to square the thing in the denominator. What do you get? If you do the calculation, you get 133.4 newtons. Now, I'd of course recommend you try punching this into your calculator yourself and see if you get this answer, because it is a little bit of a complicated calculation. You want to make sure you can calculate the right answer. So remember, those are the forces between these two. Now I have a question for you. Is there a force of gravity between A and C? There is, right? Even though B is sort of in the middle, A and B and C, are still pulling on each other, right? So there also is going to be a force F of C on A, right? And there's going to be the opposite force, F of A on C, right? So that's going to be a force as well, and we can calculate that in the exact same way, right? So A and C, okay? And what I'm going to let you do now is I'm going to let you pause the video here, calculate that force yourself. And when you do that, you should get 44.47 newtons of that force A on C or C on A. And the last question is, the only pair that we haven't done yet is B and C, right? So there's going to be a force that C exerts on B, FC on B, and there's also going to be a force B on C, right? And they're all attractive. They all, are towards each other. So let's calculate that one as well. So this is B and C. And again, I'd recommend you pause the video here, calculate it yourself, and make sure you're getting the right answer. Unpause when you got it. I got 50.03 newtons. So we have all of the pairs of forces now. Now the original question, if we remember what it was determine the net force on each asteroid. So again, net force is just if we sum up the forces on each asteroid, right? So now that we have the magnitudes of the forces, this shouldn't be such a big deal. I'm actually going to do it above just because I'm a little bit out of space. So sorry about that, but we'll do each asteroid here. So the net force on asteroid A, we'll start off with that. Well, we know we have this force to the right of FB on A, which if we look at what we calculated there, it was 133.4, right? And we also had a force to the right of FC on A of 44.47, right? So what's going to be the net force on asteroid A? Let me label this A. So F net, well, both of those forces are pushing it to the right. So if we make right our positive direction, we can just add those two up, right? 133.4 plus 44.47, what do we get? 133.4 plus 44.47, we get 177.87 newtons to the right. So that tells us that that asteroid is actually going to accelerate to the right, right? Which makes sense because both of the other asteroids are on the right and they're all going to be attracted to each other. So it makes sense that this one would move to the right. Let's do the same thing for asteroid B. Asteroid B has a force pulling to the left by that same 133.4 newtons, and it's got a force pulling to the right. The green force of Fc on B was 50.03. So what's going to be the net force on this asteroid? Well, again, if we make right the positive direction, the 50.03 would be positive, and the 133.4 would be negative, so we would subtract it. And we would end up with a net force of 50.03 minus 133.4, which is negative 83.37 to the right, or, in other words, 83.37 newtons to the left. Right? Oh, I forgot the newtons here. Right? So this one would actually accelerate to the left, right? Oh, you can't see that. It would accelerate to the left, right? Because the force pulling to the left is stronger than the force pulling to the right, so it would actually accelerate this way. And which way do you think the third one's going to accelerate? Well, I mean, both those forces are acting in the same direction, so we should be able to figure it out. Again, we have the green force pulling it to the left by 50.03 newtons, and we have the blue force pulling it to the left from asteroid A at 44.47 newtons. So both of those forces, right, if we just keep our positives to the right, it'll be two negatives. So negative 50.03 minus 44.47, get a total net force of 94.5 to the left, okay? Or if we stuck with the negative, it would have been to the right, but I fixed that there. There we go, so we calculated our three net forces. So yes, as expected, that one would accelerate to the left. So a common mistake here is when I ask you to calculate this, you forget about the fact that A and C pull on each other. You just calculate the forces between A and B and C. But remember, all of these will affect each other, not just the ones that are beside each other. So now, example 2. Can you figure this one out? So I'd actually recommend you try this one yourself. You pause the video here, try the whole thing yourself. And then I will quickly go through the solution once you've given it a try. So pause it here, try it yourself, unpause to see the solution. So here's the little hint for those of you who had a little bit of trouble starting. One thing to notice is that the force on AB should actually be the same as it was in the previous question, right? Because the distance was the same and the masses were the same. And same thing between B and C. So these forces were the same and these forces were the same. But the forces between A and C were different. Not because the masses were different, the masses were the same, but the distance between them was different, right? And the trick to this question is you have to calculate what this distance is, right? You're not given what this distance is. But if you know that this is 10 meters and you know that this is 20 meters, I mean, it's not explicitly stated that it's a right angle triangle, but you can make that assumption pretty clearly. So we should be able to use Pythagorean theorem basically to figure out this length. And the distance between it is 22.36 meters. And then if you find the force of gravity between them, it is 80.04 newtons. So now if you have that part, again, you have to try to find the net force on these asteroids. So how are you going to do that? Just as a little hint, let's start off by doing this. Let's do north, south, west, east, just to define the directions. Let's make up positive and right positive. What type of question does this make you think of? Again, start with asteroid A. See if you can now come up with the net force that's exerted on asteroid A, and see if you can do it. So pause the video here, try it yourself, and see if you come out with an answer for asteroid A. So hopefully you tried it yourself, but looking a little more closely at asteroid A, we have two forces acting on it, right? The 133.4 newtons to the right, and then this force down here that acts at an angle. It's not in any, it's not in north, south, east, west. So we need to find the angle that it's acting at, because in order to find the net force, remember what we have to do. We have to sum up all the x forces, we have to sum up all the y forces. So if you go back to your big diagram, we can use this to find out what the angles are, right? And I just use inverse tan, right, because the opposite is 20 and the adjacent is 10, to find out the angles in the triangle. So 63.43 is angle A, I called it, and 26.4757 is angle B. Actually, I should have called that angle C because it's at, asteroid C, but it doesn't matter, you get the idea. So, going back to this diagram, we know that the angle that this force acts on is 63.43 degrees inside that triangle, right? So we can calculate the x and the y components of that force. And the x component is going to be 80.04 cos 63.43, which gives you 35.8 newtons. And the y component is 80.04 sine 63.43, which is 71.59 newtons. So now you have, all the forces in the x direction, all the forces in the y direction. So now you can sort of sum them all up. So the sum of the forces in the x direction, is 133.4 newtons, and you're going to add to that 35.8 newtons. And in the y direction, we have just one force, and it's the negative 71.59 newtons. I said negative because, again, we're going to assume down is negative. So again, this represents the total forces in the x directions and y directions. So this is 133.4 plus 35.8, which is 169.2 newtons, right, in the x direction, and then negative 71.59 in the y direction. So we can draw our final triangle, right, for this asteroid, for the forces acting on this asteroid. So the final triangle is 169.2 newtons to the right, and then 71, let me draw that shorter, 71.59 newtons down. And the resultant force connects the beginning and the end, right? So this is going to be the force, the total force, the net force on asteroid A. I'll call it F net A. So of course we can find the magnitude of the net force by doing the square root of 169.2 squared plus 71.59 squared, which gives us the net force of, 183.84 newtons. Okay? That's the net force in the A direction, and we also do, whenever we give a net force as an answer, we also need the direction. So I'm going to call that angle theta there, and we're going to do theta equals inverse tan of the opposite over adjacent, 71.59 over the adjacent 169.2, to give us what our angle is there. And the angle is 71.59, divided by 169.2, 22.93 degrees. There we go. So that is our net force and direction on asteroid A. So we can write out the final answer, F net A, and I can put the arrow over the F net because now we have the magnitude and the direction. And I'm going to round this to 3 significant figures based on the question. Actually, maybe 2 significant figures based on the original question. Should have done this in the previous question too, but I'm actually going to round that to 180 newtons. And the direction is, well, it goes east, 22.93, and I'm going to round to two significant digits here, so 23 degrees south. So all that work all that work, I really didn't give you enough space on this page to do this question, because all that work just found the net force on asteroid A. So if we wanted to know the direction that A would accelerate in, it would accelerate in this direction, east 23 degrees south, right? Because it's got a force pulling it a little bit to this direction and a force pulling it a little bit to this direction. So it's going to accelerate somewhere in between, right? So seems like a lot of work, but again, you get fast at this by practicing it. So what I want you to do now, if you haven't already done it, is try the same thing for B and C. I'm not going to go through all the steps, but I will write down the answers to B and C. So pause the video here, try to find the net force on B and C, and when you unpause it, I will show you what the final answers are. So if you calculated the net force on B and the net force on C, you should have got these answers rounded to 2 significant digits. All right? One thing that maybe you did realize to speed up your calculations is on B, you didn't need to break up either of these into the components. You already have the x component and the y component because there's no forces acting on an angle. And the other little shortcut that you might have realized is for this force here, the force of A on C, it has the same components as the force of C on A, right? So the y component was still 71.59, it was just up instead of down. And the x component was 35.8, but it was to the left instead of to the right. So you could have used that to speed up your calculations a little bit. You wouldn't have to do these calculations again. Either way, I know it's a lot of work for a question like this, but it's good practice for summing up vector components and then tying in that gravity calculation as well. All right.